In developing Special Quiz 3, I ran into two problems. One had to do with assessment of the reliability of the thermodynamic properties data for the species H2S, HS minus, and sulfide ion, all in aqueous media. Data for these species are all available from the National Bureau of Standards Table of Thermodynamic Properties, a government circulated publication. But I'm not always able to find out where the data came from. I mean, the data are there. They came from somebody's experiment, I guess someplace along the line, but I don't find the citations necessary to allow me to back check on the original papers themselves from which these data were obtained. In any case, I had speculated before I did the arithmetic that the data were reliable for H2S and HS minus, and perhaps not reliable for sulfide ion. That's true. However, I also discovered that the data in the table for H2SAQ seemed to be way out of whack. So that put a pause in my special quiz development, because I hadn't expected to meet with this detour. So I had to take time to analyze that problem myself. Needless to say, I shall share that analysis with you. That's part of Special Quiz 3. So you'll see that, I believe, is question 1, with the various parts regarding the various 3 species. Then, I had in my mind the 4 questions, or 4 general questions, one of that being these thermodynamic properties of these sulfide ion sulfur-related species. And I couldn't remember one of the questions. I had it in my mind the other day. Been rolling it around in my mind for a few days. One of those questions disappeared. It's still up here. It'll come back. I don't know when. But I guess for Special Quiz 3 I'll have to invent a different question. It just went poof, just like that. I know it's hiding in there. Just won't come out. In any case, with that having been said, I'll invent a different question other than the one that I can't recall. It's hard for me to write a question on something which I can't recall and get this Special Quiz 3 to you as soon as possible. Now, along with Special Quiz 3, I shall ask that you download evaluation form sheet for your discussion instructor. Because to convince me that you should have your Special Quiz 3 examined for credit, accepted for credit, along with Special Quiz 3, when you submit it, I want an evaluation form submitted in the behalf of your discussion instructor by you, along with Special Quiz 3. Now, the evaluation form is to be submitted in anonymous fashion. So when you submit this, I'll have you bring it to class, and I'll have a labeled sheet that says stack here, Special Quiz 3. That, of course, has to have your name on it. And another stack that says, here, submit the evaluation form for your discussion TA. Their name will be on it, but your name will not. So I'm not going to take any time whatsoever to associate the name of the submitter of the eval form to the special quiz. That we do not want to do. You're anonymous in that fashion. Now, along with this, Special Quiz 3 has been tabulated as due a week from today, at the start of our last lecture class. But I will, as I always do, arrange for a review session on next week, Friday. That's this, what the hell the university call these days? Reading days? I have no idea what that means. Are there other days of the year not supposed to read? Just read on these 2 days? I don't know what that means. Reading days. I have no idea what that means. And the university giving up those 2 days as class days is stupid. Another stupid activity by a stupid administration who perpetually does stupid stuff because they never pay attention to the educational process and how it is affected when they do these stupid things. It's all on YouTube. I'm waiting for them to say something about this because I'm ready to defend myself in any open court with anybody who wants to attack me on this matter. I will not tolerate abuse of education. And that's what the hell this administration does time and again. And I don't like it. I guess that's obvious. In any case, I will ask again next week, and if you need extra time on Special Quiz 3, I'll let you wait until Friday to submit it. That's okay, with no penalty. You think you'd prefer Friday? I mean, you know, you don't have to attend the review, but if you don't, you're still going to have to submit the special quiz if you want credit for it. If you don't want credit for it, that's up to you. Okay. Well, we'll let you look at the special quiz after I develop it, and we'll ask again next week. But I don't mind extending to Friday. Unfortunately, the review session will not be here because this room will be used for a chemathon activity. I'll find us another room nearby, no problem whatsoever. And of course, after I get this room established, I will announce such to you. Be hard pressed for you to get there if I don't tell you where the room is. Now then, on with Chapter 23 activities. With the main intention being to develop a sound ability to rationalize strengths of Bronsted-Lowry acids and bases. You'll see there's one very special question regarding this issue, which is part of Special Quiz 3. The issue to which I refer is rationalizing the strengths of a series of oxoacids of phosphorus, which have very interesting relative strengths. I've not been able to find an explanation of the different strengths of these acids any place that I have so far looked. Nowhere. Can't find it in textbooks, can't find it on the web. So I'll ask you, why not? But there is a way to explain it. It finally occurred to me on thinking about this, and this is the fun of the chase. For me, this is the real fun of the chase from a selfish standpoint. Because every time I go through this, I learn more and I love it. And guess what happens when I learn more? I share it with you all the time. You betcha. So you'll have the pleasure of tackling this particular question. But to try to assist you, I will provide you with a hint. If you understand the hint, you should be able to field this question successfully. Because that's when you learn. And I want you to learn. You betcha. You betcha. All right. In any case, the rest of Special Quiz 3. One other feature of Special Quiz 3 will be to ask you to think about the unusual nature of the unpaired electron. How about that? The unusual nature of the unpaired electron. NO, simple molecule, 2-atom molecule. How many valence electrons? How many? 11. Ah! The unusual nature of this unpaired electron relates to whether or not this unpaired electron is part and parcel of the bonding environment for the simple NO molecule. You'll be asked to think about that on Special Quiz 3. And I'll direct you to the information which you need to think about in order to be able to answer the question. The remaining part of Special Quiz 3, that's the part I forgot. So I'll have to come up with something else. I will, don't worry. I got all kinds of things I can ask about. It's just that the question I had in mind flew away. It'll come back someday. I don't know when. Maybe by the time I sit down this afternoon to write it. I don't know. Every now and then these things happen. I don't worry about it. It's a good bet. I'll remember it during my sleep. That's what I full well expect. I'm not kidding. It's fun. Who cares? Now then, a couple of issues which stem from the videos that I asked you to look at. In fact, asked hell, I demanded that you look at them. I hope you did. Question 23-7. Which atom is harder to ionize, beryllium and carbon? Now, what underlies this question? Well, prior to comparing the first ionization energies for beryllium and carbon, you were asked to consider the first ionization energy of boron and beryllium. If you looked at the videos, you know what's going on here. It's also discussed in the notes, even if you didn't look at the videos. If you read what's here, it's there. Beryllium, 2s2 valence config. Boron, 2s2 2p1 valence config. The first atom in the periodic system, which in its electron configuration has a p electron. And when you look at the radial probability graphs for these atoms, what do you find out about MPD for 2p electron versus MPD for 2s? Remember what MPD is? Most probable distance from the nucleus. On a time average basis, where would you find this electron most commonly if you treat the electron as a particle? Because it does have particle qualities. On a time average basis, which electron is closer to the nucleus, 2s or 2p? 2p. So, even though boron's got a 2p valence electron in addition to its 2s electron pair, it's the 2s valence electrons for the boron atom which define its size. Because on a time average basis, they are the furthest from the nucleus. And whichever valence electrons on a time average basis are furthest from the nucleus for an atom, those are the electrons which determine the size of the atom. Horse sense ought to say, yes, it's got to be. So we go about the issue of considering ionizing boron. And say, given that the MPD for 2s electrons exceed that for 2p, we should expect based on MPD, to remove a 2s electron, which would give B single plus the configuration 2s1, 2p1. And the B single plus cation would be doubly paramagnetic, wouldn't it? But on ionizing boron, we first observe a property. It's not doubly paramagnetic. It's not paramagnetic at all. It's diamagnetic. What's that tell us? Which electron got removed? 2s or 2p? 2p! So we go back and say, after looking again at these radial probability graphs, how the hell can this 2p electron go preferentially to 2s when on a time average basis the 2p is closer to the nucleus? Aha! And then we start looking further into these mysterious properties of these critters called electrons. I love these mysterious properties, because the Heisenberg principle, which I believe to be absolutely right, in sum, the Heisenberg principle says, no matter what we do, no matter how good we devise experiments for such, or methods of observations for such, we cannot, it's impossible to know exactly the momentum and position of an electron. Because when you go to observe the electron, you have to change one or both of these properties of the electron. You cannot avoid such. So regardless of all the wisdom and smartness and all this stuff, pooled together of all the great scientists of all time and all the great scientists which shall ever live, it's electron 1 and great scientist 0. Ha ha ha. Electron wins. Ha ha ha. You can't never know what I'm like. Ha ha ha. I like that. So we go back and look at this radial probability graph. And we superimpose upon this the radial probability graph for 2s. Well, by golly, there's this yellow stuff over here, so let's draw that in with yellow stuff. And we recognize also in making these radial probability graphs that this part of the radial probability curve extends, because this is distance from nucleus going this way. Here's the nucleus. Nuke. Distance from nucleus going this way. Do these right side extensions of these radial probability functions ever touch the baseline? No. What's that mean? That means the radial probability for any electron, for any atom, extends to a position in space called infinity. Why? Because it's a damn wave also. And this wave can be every place at any time. How about that? That's why the electron thumbs its nose at all the brilliancies we have. Ha ha, you can never know what I'm really like. But back to the radial probability graph. You see this funny part of this graph for 2s? Do you remember drawing cross sections of orbitals in Chemistry 2045? If you have a 2s orbital, looks like a sphere, and you slice it right in half, right through the origin, you slice it in half. Okay, so now you got two hemispheres. You open up one of these hemispheres and look at it. What's it look like? For 2s. Remember what it looks like? Well, after you slice it in half, you got half a small sphere. That corresponds to this part of the radial probability function. What's this white encapsulation wrapped around the circumference of the sphere correspond to? What's the word for it? Because you see, I didn't draw this quite right. Because here the radial probability function does come down to the baseline. Right here. This, well, let's do it this way. This here is this circumference that I just drew around this sphere. What's it called? When a wave function goes to 0, what's that called? Called a node. What's the significance of the node? Physical significance. What probability do you have of finding the electron when it's at the node? 0, nothing. So probability-wise, it ain't there. I love this electron. It's there, but it ain't. How about that? I mean, how can you, in your mind, cook up a physical picture of what the electron really is? It's impossible. It's this particle, it's this wave, it's any place, because it goes to a position in space called infinity, when it belongs to a nuclear force field. An electron's part of an atom, and it has this probability of never finding it when it's here, even though it's there. I'm telling you what, this electron is great. It's having all the last laughs. But when we look further at this sliced 2s orbital, which we just sliced in half, we say a much larger outer hemisphere wrapped around this inner sphere. But the outer half and the inner half don't mix with each other. They're separated by this node. So this is the inside part. Here's the outside part. Here's MPD for 2s. That tells us why the 2s electrons of boron define its size rather than its 2p electron. This tells us why the 2s electrons for all the atoms following boron have their size defined by 2s rather than 2p electrons. This all comes from quantum mechanical fancy stuff. Carbon, nitrogen, oxygen, fluorine, neon. Because all of those got 2s as well as 2p valence electrons. And for all of those, the 2p electrons, on a time average basis, MPD, closer to the nucleus. So for all those atoms, the 2s electrons define size. But why in the hell is this 2p electron preferentially removed? That has to do with this component of the radial probability function for the 2s electron, which I guess, for lack of a better term, the quantum mechanical folks have decided to call this the penetration region because it's close to the nucleus. What's this penetrated through? Well, remember, what else is also here that I haven't put on this radial probability graph? What's the total configuration for boron? Total configuration for boron, electron configuration. 1s2, 2s2, 2p1. So this penetration region corresponds to there, that's better. This blue stuff, it's not even like, it's more like this. This blue stuff is the 1s radial probability function. But we don't include that in this graph because 1s electrons are not part of the valence environment. But if I want to demonstrate the real meaning of this penetration region, then what I'm showing you here is that this 2s electron has a much better ability than a 2p electron to get, on a time average basis, close to the nucleus. And when it gets close to the nucleus, it feels an average nuclear attraction which exceeds that for the 2p electron. Upshot, when you ionize any atom which in its valence configuration has 2s and 2p electrons, which electrons go first all the time? 2p, all the time. And this is why. This so-called penetration business. This is why. When you go to add electrons to the orbitals of an energy level, and you see a sign that flashes vacancy in front of 2s and 2p, you always go to 2s first, because you're more stable there. Because of this penetration business. If you got 3s, 3p, 3d electrons, you go 3s first, 3p second, and then you don't even go to 3d third, you go to 4s third. Then you go to 3d. And as soon as you go to 3d, they become more stable in 4s. It's all funny stuff these electrons do. They don't give a damn know how we think or how we understand. That's the way they behave. And it's our job to do the best we can to understand this insidious behavior. It's beautiful. I mean, I defy anybody to have a physical picture in his or her mind which is a sound representation, an accurate representation of an electron and its behavior. How do you do this? It's a particle, it's a wave, it's every place, it's no place, and all at the same time. Well, how the hell are you going to think about that and get a picture in your head that corresponds to such? Like I say, electron 1, famous scientist 0. And that, I believe, will last forever. And I love it. Because if nothing else, it means we will have to continue to learn. There's no encapsulation to the amount of human knowledge which we can accumulate. One of the greatest things of research in science is that as you do good research, which will answer good questions, you will along the way develop more good questions to be answered. The more you learn, if you're a good scientist, the more you will realize there is to learn. It's wonderful. I mean wonderful. You will never get bored. You might get frustrated and worn out and upset, but you won't ever get bored. There's no limit to it. It gets bigger, 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 bigger. The more you learn, the more you will realize there is to learn. To me, you want a truly great, enriching, wonderful, rewarding activity in which to engage in life, do science. You can't go wrong. It's great. Money, money's absurd. Money means nothing. Material things don't mean anything compared to intellectual enrichment. I mean nothing. The intellectual enrichment is with you and warms you and satisfies you all the time. I mean, somebody's in love with a car. Get out of here with that person. That's a sick mind, I mean it. Something wrong with that person. You spend your life in pursuit of money? What a sick waste of disgusting. I mean, I don't want any part of any person who acts like that. Nothing. You keep them away from me. That's cancer. That's poison. I don't want any part of it. Junk. Give me enough so I can eat well and sleep well. I got all I need. Do science. And what I learn, I do the best I can to share it with you. Because maybe you too will go on and have as much fun in your life as I have and still am having and hope to have for a hell of a lot longer. Now I'm almost 72, and if I have my way, I'll be here when I'm 172. How's that? Maybe I'll live as long as the electron. I'll travel with them to infinity. Ha ha ha. All right, on we go. Simple question. Oh, back to this. How about beryllium versus carbon? Now we got a problem. What's the problem when we get beryllium carbon as opposed to the problem in ionizing boron beryllium? Remember the component of the atom which attracts electrons. Protons, right? Because all we're really doing is talking and reflecting first on facts. I have told you the story which I just told you about boron and beryllium and all this stuff because they fit the facts. That's the bottom line dictator. The bottom line dictator in all of this is the fact that beryllium is more difficult to ionize than boron, even though boron is bigger than beryllium. That's the fact. That's the only bottom line dictator in science, not what I say or what anybody says. That means nothing relative to the fact. Nothing. But we get the carbon. Now we enrich the nucleus by one more proton, didn't we? So now we know when we ionize carbon, which is 2s2, 2p2 valence, we know we're taking away a p electron. And we recognize when we ionize beryllium, we have no choice but to take away a 2s electron. And in so doing, we recognize that boron is easier to ionize than beryllium. We take away a p electron. But boron's only got a single p electron and 5 protons in the nucleus. When you go to carbon, you got 6 protons in the nucleus. And one of its 2 valence electrons will leave. Makes no difference which one, because they're equivalent. When we convert carbon to carbon single plus. So what costs more? Ionizing a 2p electron from carbon or ionizing a 2s electron from beryllium, recognizing that now with beryllium you got 4 protons in the nucleus versus 6 protons in the nucleus of carbon. And to me, the only way you can answer this question is by doing the experiment. And if you do the experiment, you'll find out that carbon is somewhat more difficult to ionize than beryllium. So now the added proton counts more than this penetration business. And I don't know any other way. I don't see any way you could predict a priori. After you know the difference between beryllium and boron, I don't see any way you could sit down and absolutely predict that carbon has a somewhat higher ionization energy than beryllium. I don't see any way you could predict that. So we look at the facts. All right, 23.8, a simple question. What's the atom in the periodic system with the shortest 1s orbital radius? In other words, as it relates to this graph. If this This is the radial probability function for the 1s pair of electrons, let's say for carbon, who cares, okay? How does this radial probability function change, if at all, when you go to nitrogen? Because nitrogen, all atoms after helium have a 1s2 core electron pair. And there is the radial probability representation of this 1s2 core electron pair. So if I stipulate that this is for carbon, how will it change if I redraw this graph and I want it to be for nitrogen? See this MPD position? Going to move this way, right? Because now I got 7 protons pulling on it. Oxygen, fluorine, neon, and it keeps getting closer and closer. So the atom with the shortest 1s2 orbital radius, which is this, the distance from the nucleus to MPD, right there, corresponds to the atom with the largest value for Z. And I believe the nuclear physicists have now succeeded in synthesizing atom number 118, which has got a lifetime so fleetingly short that an Avogadro's number of these atoms just passed away in the number of time it took me to say this statement to you. But they've got the evidence to believe they made number 118. It's gone because it's so unstable. But it's going to have the shortest 1s2 radial probability function. I mean, not the shortest, but the one with the shortest MPD. Okay? 23.9. One more consideration regarding these radial probability graphs, just to try to see to it that you have a good understanding of what they mean when you look at them. Take a look at the radial probability graph. I think it's D, which shows radial probability function for 3d electrons overlapped on 4s. Do you see it? Based on radial probability, where shall we expect to find the biggest shrink, the biggest size gap? When I convert scandium to scandium single plus, because that involves losing a 4s electron. The scandium single plus is 3d1, 4s1. We talked about this the other day. Well, I still got a 4s valence electron here, don't I? So the electron which defines the size of scandium single plus is again a 4s electron, just like the electrons which define the size of the scandium atom itself, 4s electron. But what happens when I go from scandium single plus to scandium double plus? Well, if we simply bear in mind the rule that always holds, that when you ionize, highest n value electrons always go away first, 3d1 4s1 for scandium single plus becomes 3d1 4s0 when you go to scandium double plus. So here you no longer have any energy level 4 electrons. What does the radial probability representation of this tell you? Big shrink? You betcha. Because MPD for 3d electron, which is shorter than MPD for 3p electron, which is shorter than MPD for 3s electron, is a whole lot shorter than MPD for 4s electron, which in turn is greater than MPD for 4p electron, which is greater than MPD for 4d electron, which is greater than MPD for 4f electron, because at energy level number 4 is the first time we encounter f electrons. But that doesn't change the order of stability. The 4s electrons in the energy level number 4 are the most stable because of this penetration business. So here's the biggest shrink. Now when I get to scandium double plus, now for scandium double plus, which electrons would I argue are the size determining electrons for scandium double plus? Which electrons? This one? 3s, you betcha. Because this thing's got argon core. That's got 3s and 3p electrons in it, doesn't it? And for 3s, 3p, 3d, which of these electrons has the greatest MPD? 3s. So, if these radial probability graphs are true, the size of each and every atom in the periodic system is always determined by its highest n value blank electrons. What goes in the blank? S, you betcha. All the time. There are, as far as I know, there are likely exceptions for this statement that I made when we get to these transition metals. But that keeps with these transition metals showing these irregularities in size pattern. I mean, pardon me, there's no pattern. No trend. Okay? All right. And now we pick up with what you folks were aiming at yesterday. And I expect this is what we'll wrestle with till the end of the term. Factors of consequence, which we must pay attention to and understand. If we are going to successfully rationalize the strengths of Bronsted-Lowry acids. And how do we do this? We do this in terms of assessment of the effective negative charge density for the conjugate base of any atom whose strength we wish to rationalize. Did you get a handle yesterday on effective negative charge density as opposed to negative charge density? I invented this term, effective negative charge density, to distinguish it from absolute negative charge density because, and I'm sure you all heard about this yesterday, if I want to talk about acid strengths in water solution, and I want to consider, because that's the only solvent we're paying attention to, the relative acid strengths of these two acids, well, conjugate base of this acid is this, conjugate base of this acid is this. And this has a formal minus charge. This has no minus charge, it's a molecule. No molecules have formal minus charge. But which of these has the greater effective negative charge density? Which one of these has the stronger proton affinity, hydrogen proton affinity in water solution? Which of these is the stronger base in water solution? This thing is. This is a weaker acid than this. We know this. We've been through this in chapter 18. So the upshot of this is screaming at us. The hell with the fact that this has an absolute minus charge. The effective negative charge density of this is greater than the effective negative charge density of this. What if I put this in the mix? Another molecule. How does the effective negative charge density of this compare to this? Greater yet. Let's have even more fun. There's a doubly minus anion. How does the effective negative charge density of this molecule compare to the effective negative charge density of this doubly minus anion? Which one has the greater effective negative charge density? Which is the stronger base? This one is. So who cares that this is double minus? Can you explain this? Well, when we get done with this series of considerations, you will be in position to explain this. That's what we're aiming at. Now then, yesterday, based on progress, extents as defined by your discussion instructors, everybody looked at the charge size ratio consideration, which is the first factor we pay attention to. That allows us to rationalize the difference in strengths between hydrogen iodide on down through HF. All monoprotic acids derive from the halogen elements, the 7A elements. Then, electronegativity, which allows us to rationalize the difference in acid strengths of these four acids, which relate to each other in that they are derived from elements of the same period. Neighboring atoms of the same period, specifically period number 2. The carbon derivative, nitrogen derivative, oxygen derivative, and fluorine derivative. HF the strongest of these four acids. And we already know the facts from what we've done in chapter 18. We know HCl is a stronger acid than HF. From that you can develop the pattern, the trend. We know that HF is a stronger acid than water, so from that you can develop the trend. And you talked about these factors from an understanding standpoint. Then induction. It's an electronegativity effect, which in fact is exerted through the covalent bond skeleton of a species. You looked at these three acids, which are structurally identical. The acetic acid, a so-called substituted acetic acid, in that on the left side carbon atom, rather than 3 peripheral hydrogen atoms, you had 3 peripheral chlorine atoms. Here you go to 3 peripheral fluorine atoms. And when each of these things does its acid thing, you create a minus charge on an oxygen atom, which is now a peripheral oxygen atom. Point: if this minus charge, just developed by H plus loss, for each of these 3 parent acids, well, I had them on the board a moment ago, now we got the conjugate bases. If this minus charge stays on this oxygen, stays on this oxygen, stays on this oxygen, how will these base strengths, how will the strengths of these bases compare? How will they compare? You got an oxygen atom with a minus charge on it. That's all you got if that minus charge stays there. If the other components of each of these species has no effect on this minus charge, you've got a minus charge on an oxygen atom. Period. End of story. How would the strengths of these bases compare? They would be the same. Ha ha! But the strengths of these bases are far different from each other. Which of these 3 bases is the weakest? Because it's the conjugate base of the strongest of the parent acids. Which is the weakest? Well, I think you're not going to bet on the one in the middle. Is this one? You betcha. That's the weakest. Well, this fact is screaming at us. These fluorine atoms are exerting an effect on this negative charge. They're stabilizing this negative charge density more effectively than this negative charge density is stabilized. In turn, more effectively than this negative charge density is stabilized. That's the only way this can be a stronger base than this, which in turn is a stronger base than this. What is this effect? It's called induction. Fluorine atoms, fantastic fluorine from an electronegativity standpoint. It's a lot of fun to think about electronegativity, remember? Fun, F-O-N. Fluorine, oxygen, nitrogen, and then chlorine. But as I said, there's a hell of a lot more important compounds with nitrogen in their composition than there are with chlorine. Plus F-O-N applies to the 3 atoms which neighbor each other in period number 2. Well, fantastic fluorine, because of its greatest atomic electronegativity, does the best job of inductively stabilizing that negative charge density as if by magic. The great electronegativity of fluorine is exerting a pull on that negative charge density. It's like it's pulling that negative charge density toward itself. And as it does, what happens to the distribution of this negative charge density? Well, let's look at the structure. It's like it's being smeared. This negative charge density is being smeared toward these fluorines. Well, the more effectively I smear this, the more effectively I dilute it. The more effectively I lower the concentration of this minus charge. And the more effectively I lower the concentration of this minus charge, the more stable that minus charge becomes. And the less reactive that becomes as a base. Which is why its corresponding conjugate acid is the strongest acid of these 3 bases. We did this yesterday. And now, how about length of covalent bond skeleton? So quickly, let's look at these 2, and we'll pick it up from this point next time. Here is trichloroacetic acid. I picked on these 2 because I have data for these 2. This is trichloroacetic acid. This is trichloropropionic acid. I don't give a damn about the names, that's why I didn't write the names down. What's the difference? In each case, I've got 3 peripheral chlorine atoms to stabilize negative charge density as it is developed by induction. But here there's a CH2 group in between. So let's take away the proton, turn these into bases, and then ask the question, which of these is the more stable base? Because if these 3 chlorine atoms are as capable as these 3 chlorine atoms at inductively stabilizing this negative charge, I will for this species, because it's a bigger species, it's got a longer bond skeleton, I would for this species be smearing the negative charge over a larger bond skeleton. That would dilute the negative charge to a greater extent than I dilute the negative charge here, where I'm smearing the negative charge over a shorter bond skeleton. Okay so far? So if all that's true, this is the more stable base. Now let's give you the data. Where are you, data? Data. Ah, here we go. Let's put back the proton. pKa equals about 1 times 10 to minus 3. And we'll put back the proton. pKa is about 8 times 10 to the minus 5. Which acid is stronger? That one's stronger. So guess what happens when we extend this covalent bond skeleton length? Induction ability falls off substantially. This reminds us then that atoms, in order to stabilize electron density effectively by induction, have got to be fairly close in the covalent bond skeleton to the site of the negative charge where it has been developed. Pick it up from this point next time.